Yeah, thank you very much for the kind introduction. It's a huge pleasure being here, especially being here in person. I mean, I'm alone in this room due to pandemic regulations, but at least I'm in Dortmund. This is absolutely smashing after 2 years of just online talks. So I can finally walk around. And for those who know me, yes, I finally look decent for once. I'm very happy to present Trustworthy Federated Learning today. That's a topic that is somehow always has been at my heart, but now it's really crisp and clear. Please always ask questions, interrupt me. I would like to have that as interactive as possible. Before I start to go deep into what is federated learning and how to make it trustworthy, let me explain why I have a particular perspective on the topic, because as you might all be aware, trustworthiness is a huge topic with many implications. I only look at a certain angle, or from a certain angle at it. The reason is, as Thomas already said, that I am now leading a small research group at the IKIM, the Institute for AI in Medicine. And they have this issue that they want to do AI and machine learning on healthcare data, which just has very, very particular problems. One of them being that data is inherently distributed at hospitals, and you want to train from them, you cannot centralize. Then the individual problems are very complicated. Image classification, tumor detection is a bit easier. Then there are more difficult problems like that you have time series data and so on and so on. At the same time, my group is located in Bochum. That's because we try to build a bridge between Essen and Bochum, especially the group of Asja Fischer there, who's doing a lot in learning theory. She's a world expert on Bayesian machine learning, and we try to combine these, and my little research group is in the middle. Just before I end this ad block, we are always looking for great people. And now with that out of the way, let me go into what is federated learning and then what is trustworthy federated learning. I'm well aware that most of you are very familiar with most of these topics, so please don't be too bored, but I try to get the basics straight. First of all, that comes as no surprise, data is distributed. It always has been kind of distributed. And what we usually did is we just collected it and compiled it into an Excel file or whatever. Today, it's a bit more difficult. We have huge amounts of data that are generated from mobile phones, from cars, from hospitals and machines and so on. But the classical approach is still to centralize this data into, for example, a cloud, a data lake, or a computing cluster. So we have some communications infrastructure. We send all this data into our cloud. We pre-process it, we polish it, and then we run our machine learning algorithm to train a model. I want to call that centralized machine learning, although in this cloud, we might actually run a highly distributed, high-performance algorithm, because we still have to first centralize the data into the cloud. Now, it has been observed actually a few years back now that this comes to an end. And the classical example I love to give is that of an autonomous vehicle. Such a car generates roughly 1 gigabyte of data per second. At least that was an estimate. And if you want to transmit that, you already have a problem, because you can only submit for 37 megabytes with a 4G connection. Now you might argue, well, sooner or later we'll get 5G, and then this will be not a problem anymore. But if you look at the scale and just assume that only the cars Volkswagen sold in 2018 would submit so much data, that's 10 petabytes of data per second. This was roughly 10 million cars. This is a lot. Just to put that into perspective, at the CERN experiments combined, they process roughly 25 gigabytes per second. So this is just not doable anymore. I mean, I learned today that certain telescopes generate 100 petabytes per day. We're still like, this would be like, I don't know, 36,000 times 24 petabytes per day. So it's just not doable anymore. So for this problem, huge data sets, communication is a bottleneck, you have maybe some privacy concerns, people came up with what is today known as federated learning. Actually, the idea is a bit older, but it was then popularized by the seminal paper of Brennan McMahon and his colleagues from Google in 2017. And the idea is roughly as follows. Assume that you have a bunch of data generating devices. They thought of mobile phones, you can think of autonomous vehicles, you can think of hospitals, whatever generates data. If you have a certain computing power there, what you can do is run your machine learning algorithm on that device to produce a local model. This model will most likely be very, very bad because it only has seen the little available local training data. What you could do now is, if you have some backend cluster or server, let's call it just generically a coordinator, you can just send these models to that coordinator. And by communicating models, you often already save communication because models are often smaller than the data they've been trained on. At the same time, you preserve privacy because you never submit data. You only submit model parameters. It's not without any problems, as I will discuss later, but in general, you already achieved a lot. The only problem is now you have a huge amount of very bad models at your coordinator side. What do you do with them? Well, if you could aggregate them into a single better model, then you have one, because what you can do then is either directly use it or redistribute it back to your data generating devices and iterate this process until you achieve sufficient model quality. This is roughly the backbone of what federated learning does. It has a few very, very nice properties. One is it is fairly agnostic to the learning algorithm you use. As long as you know how to aggregate your models, it doesn't care how you got them. A second really nice thing is that it scales arbitrarily well. So you can use huge amounts of learners, and you have these nice privacy properties. Great. So why are we not done yet? Well, it turns out that for many problems that the people at Google and others did not have in mind, federated learning does not work perfectly well. And a prime example for that is healthcare. And yeah, well, okay, that's my personal perspective, but it's actually also true for other critical applications. One thing is that in classical federated learning, privacy was only of moderate concern. Yes, it's not nice if your keyboard strokes get sent to Google, but nobody truly cares. With healthcare data, the situation is a bit different. You must not share any sensitive data, and you get sued or go to jail if you do. The second problem is that, especially in healthcare, curated data sets are a high-value asset. You have set many doctors to label this data for months, and every hospital is a bit protective about those. So you're in a situation where you have many small labeled data sets distributed over the world. You might even have lots of unlabeled data like health databases, but you need actually large amounts of labeled data to build really good models, for example, for tumor detection or clinical decision support. So you are in a slightly different world. First of all, you have often smaller local data sets, you have huge privacy concerns, and the last point is that, especially in all critical applications, practitioners must trust the result. They must trust the model. Now, what we want then is a trustworthy federated learning. But as I said in the beginning, trustworthy is a very broad term. So what do I mean with that? Well, the European Commission has provided a definition of what trustworthiness could mean, and I actually like it quite well, but it's very broad. And I want to focus on three parts of that. The first one is technical robustness and safety. The second is privacy and data governance, and then transparency. And these are still very broad terms, so let me specify what I mean by that. Today I want to talk about model quality and adversarial robustness, privacy guarantees, and interpretability. So these are the three major points I want to tackle in federated learning. So let's start with model quality, because this is by far the largest chunk. And here I'm specifically interested in the theory of it, but I want to start a bit going into what you can do. So let me just explain a bit why this is a problem. For those that know federated learning, this will come as no surprise, but for those that are not that into it, it might, because in classical parallelization, what you do is you take your algorithm, you look at the independent parts, you implement them in parallel, and the result is exactly the same as if you had run it centrally, just a bit faster. In federated learning, this is not the case. The model that you get from aggregating is surely worse than if you had centralized all the data and trained centrally. The big question is, how much worse is it? And can I compensate by having more data sets? And this question is really not easy to answer. But if you want to have any shot at answering it, you need to first answer two big questions, which is, how do you actually aggregate? Now, it turns out that the simplest solution works incredibly well. And this is you just average the models. So if you have linear models, then you can look at the parameter vectors of these models and just average them. And the average is your new aggregate model. This works really well. The same holds true for neural networks. We just average the model parameters. It gets a bit more tricky with kernel machines, but even there you can well define what it means to average. The second big question is, when do you actually average? Do you train locally until convergence and then average once at the end, and that's the model you take? Or if you have an iterative solver, you can run it for a bit, let's say 10 steps, average all the models, use the average as the new initialization point, and start for another 10 rounds, and so on and so on. You could periodically average with only a random subset, or you can do it dynamically. And depending on how you do it, you get different guarantees on your model and also different quality. So let's go through it for a bit. What happens if you only average at the end? That was actually the first time model averaging was ever mentioned. It was by McDonald et al. In 2009, I think. And they showed that under very certain conditions, you can achieve the same quality as distributed gradient descent with this one-time averaging. So huge amount of safe communication, same model quality. That was great, but it works only in rare cases. And it was Shami and Srebro who showed in 2014 that in fact, model averaging at the end can be arbitrarily bad, because one bad model can drag your average away basically arbitrarily. So if you have just one bad apple in your bunch, it ruins your entire trade. What people usually do instead is they average periodically. And this works remarkably well. Here you see a very simple experiment. I think it was stock price prediction. You average every 16 rounds. And what you see here is a cumulative error plot. I like to show those because they show you two things at once. They show, first of all, convergence. So as soon as you have reached the horizontal line, you have converged. And it also shows how fast you have achieved it just by looking where you hit the y-axis on the right side. And you see two baselines. One is you centralize all the data, you pool it, you train locally, you train centrally. That's the serial baseline, and it just converges the fastest, as you would expect. And the other is you just train locally, you do not communicate at all, and you just accumulate all the errors that you make locally. And this, of course, works worse. It doesn't even converge in these 1,000 time steps. And if you average every 16 rounds, you see that it converges very quickly, just a bit slower than pooling the data. That is great. One thing you also observe is that this model actually converged roughly at time step 200, or nearly converged at time step 200, but still every 16 rounds you communicate. So in my PhD, I saw that and thought, that's not smart. Can we do it better? And the first contact with federated learning was actually trying to avoid this unnecessary communication. Before I go into my solution, the guys around Brandon McMahon and his colleagues from Google had exactly the same problem. They wanted to do federated learning on mobile devices. And if you think in Google terms, that's like millions of Android phones. And there, this amount of communication was too much. So what they set up and called later federated learning was exactly this periodic averaging, but with only a random subset of the devices. And they showed that even with only 10% of devices chosen randomly in each communication step, you could achieve the same model quality as if you had communicated with all. So that's great. It's a huge saving in communication and local computation and battery and so on, without any meaningful loss in model quality. The big problem is you again have this phase when your models nearly converge where you still communicate. And my idea a bit earlier, was to avoid it by only communicating when it is useful. Now, what does it mean to be useful? Well, the intuition was that if models are very similar, then averaging doesn't change much the system, right? But if they are very dissimilar, then averaging has a huge impact for the better or the worse. So let's only communicate when models are very different from each other. And for that, I made a simple definition. If the model divergence, basically the variance, is large, then we communicate, and if it is small, we don't. The only problem with this equation is that I need to compute the average to compute the divergence. And if I already computed the average, yeah, well, then I have communicated. That renders the whole exercise pretty pointless, right? So what we need to do is we need to find local guarantees that we can check without actually communicating. And you can do that by defining any reference point that is common amongst all local clients. A sensible choice would be the last known average, and check the distance of each local model to that reference point. And as long as that is smaller than our threshold delta, we know that the divergence is also smaller than delta. If a local condition is broken, it could be that the divergence is larger, or it could be that it's not, but in any case, we have to communicate to find out. So how that scheme in the simplest way works is we train, and if at some time step, one model has a local violation of its condition, we communicate, we average all the models, and then we can reset our reference point to the now globally known average. And we are again in a stable, valid condition. We can continue training without communication until another local violation happens. Now, of course, there are many heuristics you can do to make this a bit smarter, but that is the gist of what we call dynamic averaging. And when we compare it to periodic averaging, what you see is that for any desired a threshold or communication budget, you can get a better model, or in other terms, for the same model quality, you need only a fraction of the communication, sometimes 1 or 2 orders of magnitudes less. We also, of course, compare to federated learning, and there we see that you get roughly the same model quality with half the amount of communication. So the gist is a bit communicating with a random subset is great, but smartly communicating is actually better. And of course, you could even combine the two. We've also tried that actually with Lukas and Danny and Katharina from Dortmund to do the exact same thing, but on resource-constrained devices, if you only have integer operations. And the idea here was, can we have resource-constrained dynamic averaging? Because in Dortmund, you developed these great resource-constrained models, which are working on super low power devices. But if you still communicate too much, then because communication takes up the majority of your power consumption, then this is still bad. So can we reduce it by dynamic averaging? And it turns out you can. And what I show you here is just a rough estimate of the energy savings you do by that. And we're talking about 2 orders of magnitude less less energy consumption if you train locally on your, let's say, FPGAs or other low energy devices and only communicate using dynamic averaging. All right. That's all very nice. We also tried that in a joint project with Volkswagen to train autonomous driving functionalities. And the idea was that you have cars going around the world. They all locally train a certain functionality, and you average models between cars from time to time, and you want to minimize the communication because it's costly. If you have EVs, then it's costly in terms of battery life. If you have classical cars, it's still costly because you have to pay for the communication. And the part that I can show is this funny little simulation. It's a very simple race car that goes around the track. We had 5 of them going around the track, failing left and right, going into the lake. And what you see here is the car that resulted from training with this dynamic averaging, and it drives okay. Now, as I said, what we actually want is not only good practical performance, we also want guarantees on the model quality. Now, what we can show is that the loss of this dynamic averaging is similar to periodic averaging, so it's in the same order. And for very specific learning algorithms, in this case, convex problems solved with SGD and mini-batch SGD, you can show that you achieve the same quality as centralized learning. Now, this is great for convex problems. So with linear models, with support vector machines, you can prove that this dynamic averaging and periodic averaging as well converge to the same solution as centralized learning. Moreover, we could show that also the communication is bounded, it's linear in the number of learners, and it's bounded in the hardness of the learning problem, meaning that if you have a very simple problem, you're guaranteed to not use much communication. If you have a hard one, you may invest a bit more. The problem is that while it is nice to be able to bound the loss and even the regret, what you actually want is more like a pack guarantee. But to achieve that, we had to go beyond averaging. And what we did is the so-called radon machine. The basic insight is that, as I said in the beginning, in averaging, a single bad model can ruin your average. So why not use a more robust aggregation method? And we used this rather esoteric radon point proposed by Johann Radon in 1920 to actually prove Haley's theorem. But what it is just a point in the center of your cloud. It's like a geometric median, if you want. The nice property of the radon point is that if you compute it, you always know that two other models are worse, and you can exploit this, this fact to show that if you use an iterated version, so you compute radon points, and then you compute radon points until you are left with a single point, then this makes your model guarantees that you have for your local models exponentially better, doubly exponentially better. So what we could show is that if you have an algorithm that gives you a pack-like guarantee and you run it on your local data on your client, and you do that on many clients and then compute the radon point, you get a really good guarantee for that radon point. And then, of course, we compare to the serial, and you can show that it's a polylogarithmic, on polylogarithmically many computers, you get polynomial speed up. So that was very nice. There are two issues with this approach. One is the theoretical guarantees only hold for convex problems. This is not nice, but in general not a big problem. The second problem is that you need really a lot of clients. And just to give you an idea, in order to compute the radon point, if you have, let's say, a linear model with 10 parameters, you need 12 linear models to compute one radon point. If you want 2 iterations of this algorithm, you need 144, 12 squared many clients. If you have a neural network with 1,000,000 parameters, that means you need 1,000,002 to just compute one radon point, or 1,000,002 squared to have 2 iterations. This is, of course, an amount of devices that is impractical. Just one other kind of side topic. So one problem that you also have with federated learning, if you want any guarantees, but also practical performance, is that you have often small data sets. Classical issue in healthcare, you have in one hospital 12 patients or 50 that are relevant for your analysis. Then if you want to learn any meaningful model and so few data points, it just doesn't give any result. And if you then do federated learning and average these models, they are so bad that nothing works. So what you can instead do is what we call daisy chaining. And this is recent work, has been submitted to ICML. The idea is fairly simple. You have classical averaging rounds, where you just send your models to a coordinator, you average, you send them back, and so on. And you also have daisy chaining rounds, where you send your models to the coordinator, it permutes the list, and sends the models back. You locally train again, send it to the coordinator, it commutes and sends it back. So for each model, it is like hopping from one client to another on a daisy chain of clients, training on each one, and by that, effectively having learned on more data than just on a single device. Of course, you have to have a few tricks up your sleeve to do that privacy preserving, but in principle, you can do that. If you do that with this round point I just described, then you can guarantee that even if your local data set is too small for this whole thing to work, if you do daisy chaining with sufficiently many daisy chaining steps, then you're guaranteed that you get an improvement in model quality and in the end get a good model. We actually tried that out. So this is an experiment where we trained linear models on the SUSY data set using the radon point on 440 clients. And we just used 2 examples per client. So the absolute minimum. And we achieved the same test accuracy as centralized learning, whereas standard federated learning just fails. Of course, we did not only do that on the radon point linear models, we also applied it to neural networks, and we were able to train ResNet 18 with as little as 8 examples per client. All right. So with that, I basically come to the big elephant in the room. I talked a lot about convex problems and linear models, and that's all very nice. But what about deep learning? I mean, in the end, federated learning is mostly used in deep learning. The big problem here, as probably most of you are aware, is that deep learning is a non-convex problem. So what can happen is that you train your models locally, they run into different local minima, and as soon as you average, you land on a maximum in between. So here, any form of aggregation can not only be not helping, it can be detrimental to your learning process. So that makes it very, very hard to give proper guarantees. What people can do and have done is they can guarantee that if you average or aggregate often enough, then your model cloud that is moving over the loss surface stays so close by that it's rather an avalanche running down a single minimum and converges to that local minimum, rather than spread out and be contracted and spread out and be contracted. So what you can guarantee is convergence to a local minimum. But you have no idea whether this minimum is good. So you have no generalization bound or any other guarantee on your true error. The big problem here is that we don't even have proper guarantees for the serial case, because for deep learning, so far, the endeavors to give proper learning theoretic guarantees were not very successful. In fact, it was shown in 2019, I think, that uniform convergence bounds, one of the big classical learning theoretical guarantees, are not suitable for deep learning at all. Plus, there's this mind-boggling double descent picture that I guess most of you have seen, where in classical statistical learning theory, we know about overfitting. So your training error goes down, your test error also goes down, but if you increase model complexity, then it at some point goes up because you overfit. That's the common wisdom. Now with neural networks, the weird thing is that you can increase model complexity, and instead of just going up, the test error plateaus and then goes down again, and even goes lower than it was at the sweet spot before. So this so-called double descent means that our classical learning theory cannot explain well why neural networks work. So what we want is we want tight generalization bounds for critical applications. We want them for the serial case, and then we want to translate them to the federated case. This is a fairly unsolved problem. There's just one recent paper, I think, that achieved something of that kind. It's by Jiao Li and her colleagues, and it uses the neural tangent kernel framework to analyze averaging. But in general, it's a quite open problem. What we did is we looked at flatness of the loss surface to tackle it. So let me tell you a bit about our ideas here. The general observation that if you train a neural network and the minimum it lands at is flat, then it generalizes well, has been made already by Schmidhuber and Hochreiter in the 90s. So of course it was Schmidhuber who did it first. The observation has been confirmed by many, many experiments since then. So here's just one of ours, where you can show that if you use a flatness-based measure to predict how well it generalizes, then the correlation between that measure and the actual generalization gap is high, whereas all other measures are not that good. There was a great paper, a great survey called Fantastic Generalization Measures and Where to Find Them, where they benchmarked a huge amount of measures, and they benchmarked them on a huge amount of data sets and found that indeed those based on flatness have the highest correlation. So we know that in practice this happens, but we have no proper theoretical understanding. There were attempts to link it to peg Bayesian bounds, but this has several issues for classical deep learning. For Bayesian deep learning, it works. For classical, it has some issues. So what we did is we looked at it more from the frequentist perspective and said, okay, what can we say about one neural network that we have trained, that we have in our hands, where we know the test data set, we can measure flatness, how good will it be? And the first neat observation we made is we don't need to look at flatness with respect to all the parameters of our network. We can just choose one representation layer, one feature layer, and just regard this one and don't care about the rest. So the idea is a bit that we split our network into two parts. You have a feature extractor phi, and you have the model psi. And we only need to look at the weights from the feature extractor to the model. And the second key observation that we made is that actually flatness means that we can wiggle on our weights and the loss doesn't change. That's the definition of flatness. But that also means we can wiggle on the features in this feature representation and also the loss doesn't change. Of course, in the input space, that might translate into large noise, but at least in the feature space, we know that wiggling on the weights a bit means wiggling on the features a bit. Now, this basically links flatness to robustness against noise. One important observation here is that this all hinges on the assumption that our true label doesn't change when we wiggle on it, because you're only robust against noise if changing, or rather measuring whether your loss actually changes, requires you to know the true label at the wiggle point. And the only sensible assumption we can make without knowing the true distribution is, well, it's the same label as at our point. This link allows us to obtain a generalization bound, which roughly looks as follows. So the true error is, as always, bounded by the training error plus some term. This term depends, of course, on the sample size, as always. It also depends on the dimension of my feature layer, and it depends on that flatness term. Now, first, you can compute that bound, and you see that it bounds the actual generalization gap pretty tightly, at least here on the synthetic data set. But we can also show that this assumption that labels have to be locally flat for, locally constant for flatness to make sense is indeed the case. So it's not only because our mathematical analysis was not general enough, but we can actually see that also in practice, if we have different data sets with different degrees of locally constant labels, then flatness is a good predictor for generalization if labels are locally constant, and a bad one if they are not. And this might explain why in all the papers where flatness was analyzed, it worked very, very well on image classification data sets, because in image classification, we naturally assume that the label remains locally constant. I mean, the definition of adversarial examples hinges on this. And we know that making small changes won't change the content of the image. It also might explain why it is harder to train neural networks for regression tasks. Because, for example, SGD tends to train to or optimize towards more flat minima. If you are at a very flat minimum and you have a regression task, then this might not be the one that generalizes best. There's also a link of this flatness to adversarial examples. I mean, I guess, again, most of you know this, but just as a recap, an adversarial example is defined as an imperceptible noise I can make to a picture that my network before classified correctly, in this case as a panda. And with that noise, it says, no, that's a gibbon with even high confidence. Now, if you have a high flatness, it means you can perturb your local examples without the loss changing. So this would mean some form of adversarial robustness. The issues you have to solve here is that in flatness computation, you usually use an average overall data set, data points, meaning that still adversarial examples could hide in this average. You might be robust against adversarial examples on average, but for single examples, you might still find your adversarial examples. And this is something where we are working on. This is now joint research with Asja Fischer and her group in Bochum, where we want to use this generalization bound based on flatness to compute it distributedly in a privacy-preserving manner to finally get a generalization bound for federated learning of neural networks. Of course, only for locally constant label data sets, but still. And at the same time, we want to see how we can use it to also guarantee adversarial robustness. And just as a side note, another pet peeve of us is to do federated uncertainty estimation. All right. This is the major chunk of my talk, but I still want to talk about privacy guarantees and about interpretability. So let's start with privacy. As I said in the beginning, in federated learning, you only share model parameters and you do not share actual data. This is great, and you might say, okay, we're done. The problem is people very quickly found out that you can learn quite a lot about the data just by looking at the model parameters. So one thing you can do is you can infer whether a certain data point was in the training set just by looking at the parameters. That's the membership inference attack. What you also can do is if you have model updates, so the model before and after a training step, you can infer about the training batch that has been used. This is a huge problem for privacy, so it means sharing model parameters is not as private as we thought. There are several solutions to that. Some of them are more classical, which is basically protecting the channels, like using encrypted communication. And if you don't trust the coordinator, you might even use homomorphic encryption to prevent even the coordinator knowing the local models. There's also a more popular solution that does not rely on encryption, which is you just add a little bit of noise on your model parameters. It doesn't change your model quality too much, but it hides the effect of small subpopulations. And what you can actually guarantee is that if you add appropriate noise and keep your parameters at that, you get epsilon delta differential privacy. And this is great. You just sacrifice a little bit of model quality, but you gain privacy. And indeed, so this is one experiment from this federated daisy chaining, where we showed that with moderate privacy settings, you do not lose any accuracy at all. So that's test accuracy over time. And even with a bit more severe privacy, you don't lose much. So that's great. Differential privacy is a very strong guarantee. And just by adding a bit of noise, you basically get it for free. There's just one issue, and this is particular to, not only particular to healthcare, but there it's definitely very pronounced. One thing is that model quality is quite paramount. This is in all critical applications, but I'm not sure whether doctors would be okay with sacrificing, let's say, 5% of accuracy in a model that predicts whether to cut off someone's limb. Nonetheless, this is not the biggest issue. The biggest issue with differential privacy is more principle, and it is that it hides the effect of small subpopulations. This is exactly the idea behind it, so that you cannot infer upon single individuals. In healthcare, though, small subpopulations can be very, very important for rare diseases or for rare side effects. So hiding those might just not be the right tool here. There was even a Harvard study saying that differential privacy is not the right tool for analyzing small data sets, in this case, in particular for healthcare. There is one idea that has been proposed by Elias Dulitz and his colleagues, actually for a slightly different purpose, but it fits well here, where they said, okay, if we cannot share model parameters because they might reveal too much about our data, we could share labels. So let's assume we have an unlabeled, globally known data set. In healthcare, that's very typical. You have your hospitals, they all have their small local data sets. And then you have a global health database, like the NHS health database or the American counterpart. Then what you can do is you can train your local model. and then use that local model to make predictions on that globally known unlabeled data set, and you share these predictions with everyone else. And what you have then is a slightly different training objective that says, be good on your own data, but also agree with everyone else on the unlabeled data set, as like a co-learning or co-regularization approach. And they did that for neural networks, and they could show that they get roughly the same model quality as doing federated learning or a distributed SGD, which is absolutely great. Another advantage is that they can even use different model architectures on different devices, but they did it only for neural networks. One big issue is that they do not provide formal privacy guarantees, because that was not the focus of that paper. But still, I'm collaborating with guys from a startup called Kernostics and the Penn State Hospital. We have a good idea that sharing labels is much more privacy preserving than sharing model parameters. There's one more thing you could misuse this technique for. As I said, Elias Billett showed that you can use different neural network architectures on different devices. You can even go a little bit further. You don't have to use neural networks at all. And this brings me to the last topic of today, which is interpretability. So first of all, why do we want interpretability? If you go to a doctor and say, please do neurosurgery on that patient because black box neural network said so, he will not do it. But if you give him a reasoning saying, because this test was positive, because these blood values are higher, this biomarker is active, that is why you have to do it, he might much more easily trust your model. And one typical form of such interpretable models, the most easiest, would be a decision tree. I mean, this is one that predicts the risk for diabetes. That's so interpretable that even I can understand it. So if your age is smaller than 40 and your BMI is smaller than 23, then you're not at risk of diabetes. That's a reasoning everyone can understand. So we want to learn these kinds of models: rule ensembles, decision trees, maybe small random forests, maybe decision stumps with GLMs, whatever, but interpretable models. And we want to do it in a federated setup. The big problem here is we cannot. The reason is that all methods so far rely on basically geometric properties. You embed each of your models as a point in some vector space, and then you do a geometric operation like an average or a geometric median or a radon point or whatever. But these are all very geometric properties. And what you implicitly assume is that you can embed your model into such a vector space. With a decision tree, it's completely unclear how you would embed it into any vector space where averaging would produce any sensible decision tree. So we do not know. However, this label sharing approach might come in handy here, because if you only share labels, what you have to do then is maybe define a consensus label for an unlabeled data point, and then use all these unlabeled data points now with some pseudo labels to retrain your local decision trees. And we did some first experiments, and it actually works quite well. And we are able to train rule ensembles, decision trees. It also works, of course, for neural networks. Not as good as classical federated learning, but it works. And we're currently tweaking the algorithm. It's, of course, the size of your unlabeled data set plays a role, how you actually form the consensus. And we're analyzing the privacy aspects of label sharing. And we're doing that for chronic kidney disease prediction with Penn Medicine. All right. Now, that brings me to the end of my talk. I did a little bit of a tour de force of what I did, but I hope that in the process, I could convince you of a few things. So first of all, I hope I could convince you that we need trustworthy federated learning in critical applications, and that for that to happen, we have to guarantee model quality, privacy, and interpretability, amongst other things that we also need. Then, as a side note, dynamic communication is better than random subsampling. I showed that flatness can provide generalization bounds, but only if you have locally constant labels. and that it might help to provide adversarial robustness. And I teased that prediction sharing improves privacy, and that you can misuse it to actually train interpretable models instead of neural networks. And with that, I come to an end, and I would love to hear your questions.